Welcome back and continue our exploration of amines. We have an old reaction and we're going to learn something new about the azide group that we didn't know before. Sodium azide has the strong nucleophile azide in it. And it's a strong nucleophile because it's got anions. Yes, they are resonating anions, but this thing has a lot of charges, so it's hard to stabilize it completely with resonance. So one of the nitrogens can be a nucleophile and do a backside attack and kick off our excellent leaving group. And we make an alkyl azide with very high yield. This is a very nice reaction. And then we didn't know we could do this to an azide. We could take it and reduce it. And what happens is as you give the nitrogen hydrogens, the nitrogen here gets neutralized and then resonance here. And we pick up a proton and we have isopentylamine here. This is a nice way to make what kind of amines? They must be primary amines. Because the nitrogen in the azide gets 2 new hydrogens. It has only 1 bond to carbon. That's why it's primary. And this is a very good way to make primary amines that you did not know before. So reduction of primary amides gave amines, and I don't think I had that in our review. Review continued. I just thought of it now. One way to make a primary amine from a carboxylic acid and have the same number of carbons is to make an acid halide. And then reduce it. And the only way that works this time, lithium aluminum hydride, HCl. That's the only way that works. There's no alternatives here. So that is another way to make primary amines. This is a little more straightforward, but it does involve the same number of steps. Oh, we see our friend the squirrel here. I don't know if you can't see him out there. He's been annoying all semester. Okay, what we're doing here in our trying to incorporate this new material here is we are making an alkyl bromide from an alkene on the less substituted position. And how do you do that? That is a way back review reaction. We learned reacting this with HBr, that was one of our first reactions, doesn't accomplish this goal at all. HBr does put an H on one side and a Br on the other, but that result puts the Br on the more substituted carbon and the H on the less substituted carbon. And that's not what we want. What we want is HBr, but with a reaction that generates radicals first. So we need a radical generating molecule to be present, and peroxides are the way to do it. That's a peroxide in there. And to review that, you're going to have to go back to chapter 8. It's towards the end of the chapter. I won't make you do that mechanism again, but it's good to know that we remembered a way to make a anti-Markovnikov alkyl bromide from back in the day. And then you can do the same thing we did up here, sodium azide or maybe potassium azide. We've used DMSO today. I think we used DMF. We've used acetone. The only one we haven't used is acetonitrile. So that is the Cadillac of SN2 solvents, by the way. CH3CN, acetonitrile, polar A product solvent. And you get a nice result. Here's your alkyl azide. And H2 and PT is a nice way to reduce this. There are other methods, and that star does correspond to the previous star we looked at in our review. All of these methods are potential candidates in this star here, as well as the H2 and PT. Also works for azides. And this molecule, we're not too worried about other groups because there aren't any other groups to be reduced. So let's use one of those other options. We can use NaBH4 or lithium aluminum hydride. And you've got your primary alkyl amine. Primary amine is what I should have said. And some of you think you might have a more direct way to get from here to here by trying this and reacting it with ammonia directly to have a nucleophile that ends up being an amine anyway. And things would start off well for you because you would make that molecule among many others. And that's never a good thing. I should have circled this and called it R, so I don't have to draw it again. RCH2NH3 Br minus. There will be a small equilibrium where that deprotonates here and makes this. But I want to remind you that what you just made is also a good nucleophile. And it could react with another molecule of this. And there would be little difference between the ammonia reacting with the second molecule of this or this amine reacting with the second molecule of this. So alkylation of ammonia is not good if you want to do it only once. You're going to get another R group there. So really, I'm doing the two steps again and doing the two steps again. And yes, you'll get some of this as well. You'll even get some of this as well. Yeah, 4 of them. Alkyl ammonium ion. I guess that would only involve the first step. There's no H to take off this time. But you're repeating over and over. And the bad news is, and the answer to that question with the 2 question marks is polyalkylation is what you typically get when you use ammonia and a carbon with a leaving group. So the answer to why not is polyalkylation. You get multiple alkyl groups on your nitrogen. And that is depicted with this whole scheme down here. So not a reliable way to make an amine. You're going to get a bit of this. I don't know what, 20% yield maybe maximum. And then you got to clean it up with all the other products that you have. I would rather you go this way or go this way to make a primary amine. They are much more effective. So it's good to know. And let's do one more in this segment. And it's one of my favorite reactions. We're going to form Nitro Alkanes up here. And I really don't, you're not really responsible for this reaction. These are rather nasty conditions. Nitric acid, 300 degrees Celsius. You're not doing that at Henry Ford College. High temperatures like that with a strong acid, you need special equipment. You got to keep atmosphere out of there before these things catch fire. Whew. But you can buy these things and they're not that expensive because on an industrial scale, this is done all the time. And we have Nitro Ethane here. And it's got a new, well, the number's not new, but it's a new pKa for our table. And why is it so darn low? 10. Do you remember what I said about the nitro group? I'm going to say it again. It is the most electronegative group in all of organic chemistry. It has the charge on the nitrogen and the electronegativity of all three atoms contribute to its electron withdrawing ability. So it will stabilize anions very well. And as we saw with electrophilic aromatic substitution, it destabilizes cations with equal veracity. So nitro groups, very important. And we can take their H's off with not even a terribly strong base here. That's the conjugate base of ethanol. It'll take it off quantitatively to make our anion here. And our anion can undergo what's called an Aldol reaction. You're well familiar with that when you attack an aldehyde or a ketone with some form of an enolate. And this is it's a modified enolate. It's got nitro instead of a carbonyl. It's got a nitronil. And it'll attack here, and you get an O minus, as the mechanism here depicts. And then the O minus will pick up a proton in the next step and become an aldol reaction product. Aldol reaction product, which has a hydroxy group on the beta position, alpha being here, beta here. And we have options there. If we have heat present, we can do an elimination and create our aldol condensation product. Specifically, it's a dehydration elimination. And down here, we're going to go with that and react it with H2 and PT. And we get our NH2. Don't react this with H2 and PT. It will become a CH here and a CH2 here. I don't want that. Clearly, I want just the amine down here. And reduction of nitro compounds comes into play again. We have to know them. And then we're going to practice this before we take our next break. I've got your isobutyl nitro group. It has a pKa of 10. Got a strong base here. It's going to take that H, generate an anion on the alpha position to the nitro. Same as this one here, from the ethyl, nitro ethyl, to this anionic nucleophile. And it's going to attack a ketone this time. Ketone here. We don't have an aldehyde like we did up here. We can combine our steps. And lone pair here in the second step. And we'll just say, why don't we just say blue second? Do you have to really write red first if you're saying blue second? How's that for saving a little time? And we got our blue, and it's going to grab an H from the solvent, which happens to be right there. And you're going to get this. You're going to get this. Got it drawn already. Aldol reaction product. And we're going to do an elimination down here. So we want the mechanism. And I saw a couple people on our last test. They wanted well, you can't take an H off this carbon here, but on the test, some people tried to take an H from that carbon. That's not the carbon you take H's from, either in the first step or the next step. It's the same carbon. It's alpha. A reminder, it's alpha to a nitrogen pi bonded to an oxygen. Strong base. Take that H. Generate an anion. On which position? The alpha position. Here we go. Oh, I'm not doing that. I was doing an aldol in my mind, wasn't I? We're doing the elimination. It's the second part of the aldol. Grab the H, make a pi, hydroxide leaves, and you've generated your alkene. Sorry, brain incident there. Forgot where I was going. And in this one, I just want to reduce my nitro to an NH2, and I have no other functional groups that can be reduced. So I could just use my H2 and nickel and call that one done deal. Or H2 and PT works too. H2 PT, H2 nickel, not options if you have a alkene, but they're perfectly fine if you don't. And there you have a nice beta-hydroxyamine, or a beta-amino, if you want to describe it that way, a beta-amino alcohol. You'll see both descriptions in organic and biochemistry. Beta-hydroxyamine. That's from the amines perspective, or beta-amino alcohol from the alcohol's perspective. And we're going to leave it at that. And it looks like short segment after long segment gives us a nice break. And we're going to look at these beta-hydroxyamines a little more fully very shortly. So I'll see you in a few minutes.